Kyle. In this video, we'll be talking about differentiation and what it's used for and where it can be applied. So the plan of the video is to introduce what differentiation is, to talk about what it's used for, and to introduce some examples of these particular uses. So differentiation is basically how much does one variable change with respect to another variable, i.e. finding a rate of change. And this can be as simply as doing it between two variables y and x. We can use differentiation to find out how y changes as a function of x. It's useful because it allows us to find solutions to problems and allows us to calculate minimum and maximum values and how they change or how they don't change. In this video, we'll be focusing on power law, which is the simplest form of differentiation. And it's basically, if you have a straightforward linear function, we simply multiply by the power of the variable and take away 1 from the power of that variable. So if it was y equals x, multiply by the power, take away 1 from the power of the x. The next step up is chain rule, and this is used for composite functions. So a function of x stuck in another function of x. And it's straightforwardly, it's usually applied to differentiation by substitution. If I have two functions of x that are multiplied together, I can use product rule. In the same vein, if I have two functions of x that are divided by one another, I can use quotient rule. Like I said in this video, we'll be focusing on power rule, which is simply multiply by the power, take away 1 from the power. So in what scenarios is differentiation useful? You don't know? Well, let me tell you. One of the main things differentiation is useful is for mapping out and graphing functions or relationships. This leads to finding stationary points, minimum or maximum values, and that therefore leads on to solving practical problems. Now, we're going to go through some examples of graphing functions, finding stationary points, and solving practical problems. So our first example would be to use differentiation to help us graph functions. So say we were tasked to draw this curve. How would we do it? Well, our mode of operation would be to first of all find the critical points, then differentiate the equation once to find the stationary points. This allows us to visualize where the graph turns and allows us to draw the graph accurately, basically by lining up, by connecting dots. Okay. So let's first of all write out the curve again, and note that the value 12 would be the y-intercept. That is where the graph passes through the y-axis when x equals 0. To find the x-intercepts, you can use a number of techniques. I just chose factors of 12 and picked out the ones which multiply together to give 12, and this gives me the x-intercepts where the graph passes through the x-axis. So in order to fully shape the graph, we should differentiate once to find the turning points. So here I've written it out again, and I differentiate it once using power law. And a turning point is where there is no change. So I set f dash x equal to 0, and then I solve for value of x. Essentially, what I'm doing is that I'm now solving a quadratic. Now, because this isn't a simple quadratic to solve, I'm just going to straight away use the quadratic equation, where if you have any quadratic in the form ax squared plus bx plus c, you can use the equation below to find out what the x values would be. I have two x values because this is a third order polynomial, so there's going to be a maximum of 2 turning points. And I say that the function is stationary at these 2 x values. I plug those 2 x values into my f of x, and that gives me my y values, and that gives me my coordinates of the stationary points where the graph turns. So I've got my critical values, my x-intercepts and my y-intercept, and I've got my turning points. All I do now is basically connect the dots. So this is an example of me having drawn the graph using a graphing calculator, and as you can see, I've just connected all the dots. I have my y-intercept at 0, 12, I have my x-intercepts at -1, 0, 3, 0 and 4, 0, and I have the coordinates of my turning points where the graph turns. And I've basically just connected all the dots, and this is my curve. This is my graphed curve. So let's consider more closely how stationary values can be important into solving problems. In this particular problem, we have an expression which tells us the cost of a car journey, which is the expression you see here. So the above equation describes the cost C per kilometer of a car driving at velocities more than or equal to 5 meters per second. The questions are, at what velocity V is the lowest cost C of driving, and what is the minimum cost of a 250 kilometer journey? We should find the velocity V, which results in a low cost, then multiply it by the total distance, which will result in the total cost. So what I've done here is that I've quickly drawn out the curve and differentiated it once using power law. Because I want to find the stationary value, I set it to 0, and then I solve for V. And that gives me a value V of 20 meters per second. When I put that back into the original expression to get the cost and multiply it by 250, I get a total cost of a car journey, £30, if I drive 250 kilometers. So it's quite straightforward. If I graph this function, you can see where my minimum point is. And you can see that if I'm driving at 20 meters per second, then the cost of my car journey, or the cost per kilometer, is 12. And if you do the math, when you multiply 12 by 250, you get 3,000, but because this is pennies rather than pounds, it would be £30. Lastly, we're going to look at actual practical problems. So here's the question. To find the least area of a sheet of metal such that it creates a cylinder of a volume of 2000 pi. That's pretty difficult, is it? No, it isn't, because we just need to find the minimum surface area, and we can do this using differentiation. Because this is a more involved problem, we are going to do it in real time. So in this problem, we are going to use our expressions for the volume of a cylinder and the surface area of a cylinder in order to find the minimum surface area, which will lead us to a value of R, which gives us that minimum surface area, and that will give us the minimum surface area of sheet metal that we need. So we've understood that our volume is 2000 pi centimeter cubed. Now the volume of a cylinder is equal to pi r squared h, and we set that equal to the volume which we've been given. The surface area of a cylinder is going to equal 2 pi r squared plus 2 pi r h, and I'm going to box those in red to make them pop. Now we're going to make a substitution, well, a rearrangement and then a substitution, because sheet metal, we're using that in terms of area, whereas our surface area of a cylinder is in area, but it has a height in it. You don't really have a height of sheet metal. So what we're going to do is that we're going to rearrange our expression for the volume of a cylinder and basically eliminate h from both equations, just so that we've got our surface area varying only as r rather than as both r and h, which makes it a lot more difficult to solve. Okay, so I've made h the subject, and I'm going to substitute that back into my expression for the surface area of my cylinder, and that's going to give me an expression of surface area equals to 2 pi r squared plus 2 pi r, all multiplied by 2000 over r squared. Now we want to find the minimum surface area and the value of r that gives that minimum surface area, so we should differentiate once to find the stationary value, which is basically the minimum or maximum point. In this case, it's going to be the minimum point. Now the notation that I'm using is ds over dr. You can use f of s, well, not f of s, f of r, since s varies as r. Whatever notation is more convenient for you. In this case, I'm going to use ds over dr. And remember, we're using power law, so it's going to be multiplied by the power, take away 1 from the power, so 4 pi r minus 4000 pi over r squared. And we have stationary values where there is no change in the function, so where ds over dr equals 0. So there's no change in the function. That means we have reached a stationary point. and that stationary point may be either maximum or minimum. So we set that equal to 0, and because r is the only variable, we make r the subject, and we solve for r. And that should give us a value of r equals 10. So the value of r that creates the minimum surface area is going to be 10. Right? And we take this value of r and we plug it back into our expression for surface area to find out what the minimum surface area would therefore be. We found out what the minimum radius is of the cylinder, so what value of surface area will that give us? So we take r equals 10 and we substitute it into S, our expression for the surface area. Not the one with h, the one which we've removed h from. So that's going to be 2 pi r squared, which is 2 pi 10 squared, plus 2 pi r times 2000 over r squared, where every r is a 10. And doing the math quickly in my head, that's going to be 600 pi. Yep, 600 pi. Okay, so the minimum amount or area of sheet metal that you require is going to be 600 pi.